Okay, it's our pleasure to have Professor Sudip Bhattacharya from the Tata Institute of Fundamental Research in Mumbai as our colloquium speaker today. Thank you for joining this special colloquium at this unusual day. So Professor Bhattacharya did his undergrad from Scottish Church College. We actually have a colleague who is very, I forgot, but he's probably very almost close to a batchmate. So then he's the master's from Jadavpur University, and then he joined IIA as a PhD student, but he was in the JAP program. So we were just discussing that the JAP program is a joint astronomy program where a PhD student can work with faculty members at different institutions, particularly in the Bangalore area, where there are many, because there is Indian Institute of Astrophysics, there is Indian Institute of Science, there is Raman Research Institute, there is ISRO, all this. And Sudipta was just telling me that he might be the researcher or JAP student who utilized the JAP program most, because he worked in all of these institutions. Sometimes in the daytime he worked in RRI, in the nighttime he worked in ISC, and then didn't really sleep. And that's how he became a famous professor. No, he slept in the morning. So after his PhD, he went to University of Maryland in College Park as a postdoc, and then continued in the same area as a postdoc in the NASA Goddard Space Flight Center. And then after that, he came back and became a faculty member at TIFR, where he has been there since then. And so this, I sent some of you this already, but he had a very interesting result a few years ago where there was various press releases about that. And I really like that title, that he detected a bacterium-sized deformity in a neutron star, which is 4,500 light years away. So, so that's what I'm hoping that most of his talk will be related to that. So without further delay, Professor Bhattacharya.
Did he have an official advisor?
Yeah. So there is long story.
Yeah.
So I'm going to that actually.
It's fine. That's the boss.
Yeah, generally it works. If not, then the okay. So maybe just change the slides from there. Someone. From just clicking on it. Yeah, it works if we example. Yeah, go ahead.
Let me start. Good afternoon. So I'll give a talk on this continuous gravitational waves from spinning neutron stars. Now these gravitational waves are very exotic phenomena. These are basically the waves or ripples in the space-time itself, which is very mind-boggling. And this was, of course, theoretically kind of proposed. It's from general relativity. But for a long time, this phenomenon was not detected. Only in last few years, gravitational waves have been detected from the mergers of many neutron stars and black holes when such compact objects like black holes and neutron star merge with each other, then they kind of create a huge kind of wave or disturbance in the space-time itself. If the space-time is like a, if you consider a pond, there is water, there is ripples, and space-time itself is the water. So there's a kind of ripples in the space-time. However, such gravitational waves from mergers are very short-lived because the merger process takes only about a second. So we can observe an individual phenomenon like this for of the order of a second, sub-second typically for two black holes. However, there are some sources. For example, if a neutron star, and I will talk about neutron star after this, if a neutron star which is spinning around an axis which is perpendicular to the screen is slightly deformed like this, very slightly. You see that this is 20 kilometers and this is about a few micrometers. So very slightly deformed. Then it is expected that such sources will emit gravitational waves continuously. And naturally, it is of much interest in the physics and astrophysics community. However, this kind of continuous wave has not been detected so far. Several groups internationally are trying to detect it. And therefore, it is very interesting, and I will show that for this particular neutron star, ESR J1023, for this source, not from gravitational waves, but from electromagnetic observations in various wavelengths, in X-ray, gamma ray, optical, and so on, radio, one can infer that this source is slowing down in such a way that it should emit gravitational waves continuously. And this paper I published here in monthly notices of Royal Astronomical Society 4 years ago. And just to, is actually the second slide.
Yeah, that I actually changed that slide at that time.
It doesn't matter.
Yeah, go ahead, but we can try once. You can just see. We're just changing that.
So, yeah, so as soon as the paper was submitted to archive, just to tell about the importance of the topic, some of the leading groups like this LIGO-Virgo Continuous Gravitational Wave Group and Independent Research Group in Max Planck, they are trying to detect such continuous waves. So they were very interested, asked me to give talks in a matter of a week, present this result. So this shows the importance of this topic. Now, I simply have to change from here, right?
Yeah, the bottom and no.
Yeah, so then I should need to go from this side.
Why is this not working? It works every day.
It's fine. Keep it close.
So battery is possible.
Yeah, I mean,
Yeah. So here is the plan of the talk. So first, because it is a colloquium, I will give some background, mostly about neutron star, which is an extremely important and interesting object in the universe, and a little bit of continuous gravitational waves. And then why I choose this particular neutron star. Then this source shows complex observational aspects, which I will describe, and the problems to understand such objects. Then our formalism, then implication of the formalism, and finally the constraints on the mass quadrupole moment of the neutron star, which is a technical term, basically means the asymmetric distribution of mass, because of which gravitational waves are being emitted. Yeah, so first the background. Neutron star, a neutron star is created when a massive star dies by a supernova explosion, a huge explosion like this, and its core collapses to become a neutron star. It is technically a dead star because there is no fuel to burn like normal stars, but it is, as we will see, more alive than a normal star. It shows so many interesting and important effects and observations. It's more alive. So in a neutron star, more than one solar mass is crammed into a sphere of the size of a city, like this. The radius is typically 10 to 20 kilometers, mass is more than a solar mass, core density is 5 to 10 times the nuclear density. And it is cold, meaning it is degenerate. The physics people of course know what degenerate is. So such matter cannot be created in terrestrial laboratories. This part of the particle physics or high energy physics can be understood only by studying neutron stars. So it's a natural level. Magnetic field can be 10 to the power 7 to 10 to the power 15 Gauss. Such magnetic field cannot be created in terrestrial laboratories. Some of the neutron stars, which we call millisecond pulsar, can spin 200 to 700 times roughly in 1 second around its own axis. So some of the most extreme conditions of the universe exist in the universe, and therefore, as I said, it provides a natural laboratory to study some of the aspects which cannot be studied in terrestrial laboratories. For example, what are the properties of relatively cold matter at a density of 5 to 10 times the density of the atomic nucleus? Here, we do not know what is there actually. Is the neutron star a core? If the core is a bag of 10 to the power 57, for example, free quarks, are there new types of particles? So this is a fundamental question of physics, and to answer this question, we need to measure the mass and radius of the same neutron star. Another thing is that to study the strong gravity. Now, how one can call something a strong gravity? So there are two ways. So in x-axis, we have plotted gm by r. M is the mass of the object, r is the distance from it or size of it basically. Gm by r, as you know, is the gravitational potential. Y-axis gm by r cube, which is a measure of the curvature of the space-time, which comes from general relativity. Both are in log scale, and in this plot, we are showing various objects of the universe. For example, this is our solar system. This is a main sequence star like our sun. This is white dwarf. This is our Milky Way galaxy, starting from the edge, goes up to the center, the supermassive black hole. This is here a stellar mass black hole, and here is the neutron star. Now you can see that in both ways, and both are in log scales. So you can see that the strength of gravity around a neutron star is supreme. It's far more than most of the objects in the universe by many orders of magnitude. So neutron star is the ideal object to study the strong gravity regime and to test any theory of gravitation such as general relativity. So there is possibly no branch of physics that is not useful for neutron star study. Any branch of physics you can apply to neutron star. Here from center to surface, the density changes by 14 orders of magnitude. This neutron star is relevant for example, astrophysics, gravitational physics, nuclear physics, high energy physics, and even solid state physics, because neutron star crust is the strongest known solid in the universe. It's many orders of magnitude stronger than steel, for example. Neutron stars can come in many incarnations. For example, they emit in all electromagnetic wavelengths from radio to gamma rays. They are also very important for multi-messenger astronomy because they emit not only electromagnetic waves, they emit neutrino, they emit gravitational waves. They are very important for many branches of astronomy. For example, the first exoplanet, extrasolar planet, was discovered outside a neutron star. So here are some examples of various incarnations of neutron star. This is, for example, famous Crab pulsar and Crab nebula. This is a neutron star, very newly born neutron star, only 1,000 years old. And here is a relatively old neutron star, which is Geminga pulsar, which is speeding through the interstellar medium, and which creates the shock and hence the X-ray emission. All are in X-ray. These photos are in X-rays. And then neutron star can have a companion. A normal star can be the companion of the neutron star. And from the normal star, matter can flow towards the neutron star via a disk called accretion disk. And from the central part of the disk, X-ray can be emitted because the temperature of that portion of the disk, central part, can be 1,000,000 Kelvin. So these objects can be seen in X-rays, and they are called either low mass X-ray binary or high mass X-ray binary. I will focus a little bit more on low mass X-ray binary because the topic I am giving talk on will be a low mass X-ray. So in a low mass X-ray binary, so matter flows towards the neutron star via disk. This matter has huge angular momentum. As you know, angular momentum is conserved. Any momentum is conserved unless there is a force or torque. And therefore, neutron star gains a lot of angular momentum. And therefore, it spins up. Because it spins up, it spins very fast. And therefore, neutron star in such low mass X-ray binary systems spin very fast. And some of them can be seen as accreting millisecond X-ray pulsar. X-ray because they emit in X-rays, accreting because they are accreting matter from the companion star. And millisecond pulsar because they give intensity pulsations, they show intensity pulsation, and the period of this pulsation is of the order of a millisecond. So how this pulsation happens? When we observe this pulsation, neutron star has a magnetosphere. It's the say a neutron star is roughly a magnetic dipole, and it has a magnetosphere. These are magnetic field lines, and matter comes via a disk like this in the equatorial plane like this. It comes and ultimately it may stop by the magnetic field when the magnetic field is strong enough, or the accretion rate, the amount of matter that is coming is not that much. Then it can be stopped by the magnetic field, magnetosphere here. And it is stopped at a radius which we call the magnetospheric radius Rm. We also call it Rin. Rm and Rin are same during this stop. Rin means the inner edge radius of the disk. So up to this point, disk is extended. After that, the matter from the disk is channeled by the magnetic field lines and falls on the magnetic poles of the neutron star. And so hotspots are created from which X-rays are emitted. And since the star is rotating around its own axis, sometimes we see this hotspot and sometimes we do not, or at least we see partially. Therefore, we see a fluctuation in the observed X-ray intensity, a regular fluctuation. And that's why these are called millisecond pulsar, because these stars are spinning very fast of the order of millisecond period. Therefore, we call them millisecond pulsar. When such pulsation can happen, when this matter can fall onto the neutron star. However, there is another characteristic radius called RCO, which is the co-rotation radius. I am not describing it in too much detail, but it is the radius where the angular speed of the accreted matter in the disk is same as the angular speed of the neutron star and its magnetosphere. If the disk is outside RCO, which means Rm is greater than RCO, then matter cannot be accreted onto the neutron star because it gains angular momentum from the neutron star, matter is just thrown at it. So we would not see any pulsation, X-ray pulsation in such case. We expect to see X-ray pulsation, and remember this because we will use this when Rm or Rin, that is inner edge radius, is less than RC. So that we will use. Now coming back to gravitational waves, I have already mentioned that if neutron stars merge, then huge gravitational waves may be emitted. Not only gravitational waves, heavier elements, for example, gold, are created by this merger. So we owe our gold and possibly our existence to neutron star mergers. Neutron stars are such important objects. But a neutron star can generate gravitational waves also in other ways. As I mentioned, continuous gravitational waves. This is not continuous, this is transient. It lasts for example, of the order of a second. But neutron star can also emit continuous gravitational waves. So as I already mentioned, neutron, this is a neutron star spinning around Z axis. Of course, the Z direction radius is little smaller because of the centrifugal force, but that doesn't matter. That does not create a gravitational wave. What can create gravitational wave is perpendicular direction, perpendicular plane, the two perpendicular radii, P and A, if they are not exactly same. Then there is an asymmetry in the mass distribution. Technically call it math quadrupole moment, non-zero. Then it can emit gravitational waves. And these gravitational waves can slow down the neutron star spin because a torque is applied on it. This is the expression of the torque, where nu is the spin frequency of the neutron star, nu dot is the rate of change of the spin frequency, and GW denotes due to gravitational wave. There could be other reasons, for example, electromagnetic radiation, the spin down can happen. So this is due to gravitational wave. I is the moment of inertia of the neutron star, and the mass quadrupole moment Q is defined as I into epsilon. I moment of inertia, epsilon is the ellipticity, where ellipticity is basically fractional mismatch between these two radii perpendicular to the spin axis. So such neutron star should emit gravitational waves continuously, which have not been detected so far, but an indirect way to infer continuous gravitational waves, which we do here, is to estimate the contribution of the waves to the spin down rate nu dot of the pulsar. But so far it could not be reliably done before, for example, my paper, because the neutron star can spin down, expected to spin down due to electromagnetic radiation as well. Neutron star has a dipolar magnetic field. If it spins, then there will be the electromagnetic radiation, and that is the source of neutron star spin down, which is generally accepted. So in addition to that, if there is also a component due to gravitational wave emission that we do not know, that is very difficult to find. So that's why it could not be reliably detected or inferred. Now, the next topic, why I choose this particular source, PSRJ 1023. So, neutron stars, accreting neutron star in low mass X-ray binary system can have two states. One is when it is accreting. Here is the center of the neutron star. There is a low mass star. Matter is coming through an accretion disk. Matter is falling. There can be jets, etc. So, in such cases, there no pulsar wind is expected. On the other hand, if the accretion rate stops or accretion rate is very low, then because of the pulsar wind, that is the particles coming out from the neutron star along its open magnetic field lines, these are pulsar wind which emits a huge amount of energy, this shown in green here, that can stop the accretion, and therefore this phase, in this phase we can see the pulsar in radio phase, radio pulsar phase. So RMSP is radio millisecond pulsar. So this is the radio millisecond pulsar phase, and this is the low mass X-ray binary phase. So when accretion is happening, then usually the radio emission is not detected here in this phase. Now, of course, we think that for all neutron stars, these two states can be seen, but it's not the case. So far, only for 3 millisecond pulsar, we have found both the states. And these pulsars are called transitional millisecond pulsars. And that's why they are very special. Only 3 of them have been found. Yeah.
So that means when you say that both the states exist for these 3 systems.
Not simultaneous.
Yeah, definitely it's not simultaneous. Then you actually monitor it for a
That's right.
longer time period, and you to see that this radio things coming, and then
Yes, that's right. In a few years.
Yeah, in a few years.
Of course, this state can change. People have found in a few weeks.
Yeah.
So we choose one of them, this source, PSRJ23, and the reason is the following. This PSRJ23 is an ideal and unique source to estimate the neutron star ellipticity. Remember that we need to find out the contribution of gravitational wave to the spin down rate, because there is another major contribution that is due to electromagnetic radiation. And this source is ideal because this is the only MSP for which the spin down rate has been measured for both RMSP and LMSP state. That is radio millisecond pulsar state and accreting state. For both of them. For other two transitional pulsars, it has not been done. So, however, this particular source shows many complex observational aspects from radio to gamma rays. So, it's a mess which, when not fully understood, could introduce systematics, making our conclusion unreliable. So it is everywhere in astronomy in most cases. So there are so many uncertainties, and so because everything is out of our reach, that is there. We cannot do experiments. We cannot change anything. So there's and this source is particularly notorious, shows so many unusual things. So one could think that if we do not understand all these things, how can I reliably conclude anything from this? So therefore, in our formalism, we rely only on angular momentum conservation and energy conservation, which are the basic principles of physics and should be valid irrespective of observational aspect. That's what we assume. And then I describe these problems and various complex observations. So to begin with, its mass is more or less known with some uncertainties. Mass of the neutron star in this particular system, TJ23. Its distance is known. PC is parsecs. 1 parsec is 3.26 light years. And spin frequency is quite high. It spins around its own axis 592 times in 1 second. RLC, LC is the light cylinder. RLC is the radius of the region, the sphere, which is the size of the magnetosphere of the neutron star, beyond which the field lines, magnetic field lines open up. So magnetosphere is up to RLC, which is about 80 kilometers for this source, because it depends only on the spin frequency, so we know exactly. And RCO also, that the co-rotation radius, remember, I remind you again, the co-rotation radius is the radius from the neutron star where the angular frequency, angular speed of the neutron star and its magnetosphere is same as the angular speed of the rotating matter in the accretion disk. And for pulsation, the Rin or Rm, that is the inner edge radius of the disk, must be less than RCO. So that's why RCO is important, and we know RCO with some uncertainty because it depends only on mass and spin frequency. And then there are the real things. We have measured the nu dot, that is rate of change of spin frequency of the neutron star. Nu is the spin frequency of the neutron star. Nu dot is d nu dt, which is the rate of change of spin frequency of the neutron star. One in the radio pulsar state, another is the accreting state. Both have been measured. And we see that this is, of course, these are negative because spin down. This is, the magnitude is 32% more than the spin down rate of the RMSP in the LMXD state. So there is an increase of a magnitude of 32%, which is in number huge. It's 10 to the power 31 in CGS unit. So it is not easy to provide such a torque, extra torque suddenly in a matter of days and weeks. And that's what happens here. What is the source of this torque? Because angular momentum is conserved, there must be some torque on the neutron star. What is it? This is a very difficult to explain. And then this is the luminosity or power. L is the luminosity of power, that is energy emitted per second in gamma rays in both the states, radio states and accreting states. In radio state, this is 1.2 into 10 to the power 33 hours per second. In LMXB state, it has been measured in this range. So there is a huge increase in the LMXB state. Again, there is a huge increase of power in the accreting state. And just to put in context for the students, that the luminosity or power of our sun is 4 into 10 to the power 33 hours per second, which means suddenly in a matter of days or weeks, 1 or 2 suns have been added. So that is kind of mind-boggling. Where do you bring this power from, extra power from? 5 to 10 seconds.
So this spin down thing, is it for every time it is low mass exabyte, it is the same? Or because it changes over time, correct? Sometimes it is low mass exabyte, sometimes it is regular.
So it has not been observed many times because it has been observed only a few years ago, detected. And this radio nu dot RMSB has been measured only once during certain period. LMHB has been measured in X-rays once, and that's I consider. Recently, it has been also detected in optical, and somewhat different value has been found. But still, it is greater than this radio. So not many times one, because it requires a lot of very sensitive observations. For a long time, one has to observe and one has to integrate. So this could not be done so far because it has only a few years ago it was just
much easier to do.
Yes, radio was done. Radio is much more accurate.
So radio times always it is the same.
No, it is in. That's what it says. You cannot see both the radio phase and actinic phase simultaneously.
But at the radio phase, it's always 1.89 times.
It was in the radio phase a few years ago, about 10 years ago, and since then it is always in the actinic phase. So it can change anytime. Then we can again measure radio.
So for the last 10 years,
Yeah.
it's in the LMHB phase.
Yes, about. And then this is about the spin rate, radio, etc. and gamma ray. Let's consider X-ray now, X-ray observation. So we are considering all aspects. This is a very special kind of source. So X-ray, you see that this is the X-ray light curve, which means the intensity, X-ray intensity versus time. Time is given here in kilosecond. Now you see that this is the X-ray count rate. So it doesn't matter, it's intensity versus time. And you can see there are two clear states. So modes, rather modes, we call it modes. It's a low mode here, shown in blue, and high mode here, shown in black, and there are some flares as well. And low mode, always the intensity is something like this. High mode is always intensity something like this. And flaring mode, the intensity can vary. So you see, the point is there are two stable modes. So this does not happen usually for any other sources. Only one more transition pulsar is there, kind of twin of this one. For this we see this. But for other sources we do not see such stable high modes and low modes. They can fluctuate. But here it is just very stable high modes, very stable low modes. So this is very interesting and we do not understand why it happens. What makes them? Because they are stable, there must be some very strong physical reason behind it. So you see that so the accretion disk of the low mass X-ray binary, the source has an accretion disk in the low mass X-ray binary phase. That has been confirmed from optical observation as well, because there was some H alpha emission line, etc. What we expected. And from X-ray spectral fitting, we can fit the spectrum. Spectrum is basically intensity versus photon energy or light wavelength. So that is called energy spectrum. So by spectral fitting, we can extract various information from the source. So from the spectral fitting, people have found the inner edge radius of the accretion disk is about 21 or 26 kilometers, something like this, with some uncertainty. Okay. Now, this is very interesting. This is independent X-ray observation. And you see, this means we know the RCO already, and this means this from this independent X-ray observation, the RE can be less than RCO, which means we can expect pulsation. And another important point here, which I did not mention, that we see X-ray pulsation only in the high mode. So this high mode and low mode business are really physical. Something very strong physics reason is there. We see X-ray pulsation only in high mode, not in low mode. So what we find that in the high mode, this is the high mode result. The high mode, the RN can be less than RCO, and for that we do expect pulsation. That's what we see. So this is kind of understandable. But there is a problem. The problem is this. We, unlike any other source, for this particular source, we can also observe this source in the radio pulsar phase. And for the radio pulsar phase, we measure the new dot RMS speed. That is the rate of change of the spin frequency of the neutron star. Now, typically what people do, they consider this slowdown in the radio pulsar phase is entirely because of the electromagnetic radiation plus the emission from the pulsar wind. So magnetic dipolar radiation plus pulsar wind. From this, due to this, it slows down. If we put that expression here, the magnetic dipole radiation, for example, this is the expression of that. This is the expression of torque, and for magnetic dipole radiation, this is the physics expression. If we do that, we find a magnetic dipole moment of the order of 10 to the power 26 Gauss centimeter cube, which is very high, which indicates a very high magnetic field, that is 10 to the power 8 Gauss magnetic field, roughly. However, we measure the X-ray luminosity for the source, so we know that roughly that how much matter is coming out. We know because the source is very faint in X-rays, quite faint compared to many other similar sources. The accretion rate is relatively small, and if this magnetic field is so high, with this accretion rate, the accreted matter cannot come to the close to the neutron star. But here, in the previous slide, we said that it comes close to the neutron star, and we could explain the X-ray pulsation, etc. But now we see from the independent observation of radio phase that the matter, because the magnetic field is so high, accretion rate is so low, we do not expect the matter to come close to the neutron star. So that is the problem. So now this is one problem, and this is another problem about gamma rays. So why this increase in gamma rays? An energetic outflow from the pulsar system should power the gamma rays. So gamma ray can come, this pulsar wind, huge pulsar wind is coming out, and that could create gamma rays. But why this power is increasing in the accreting phase? Typically, people think that it could decrease in the accreting phase because this accreted matter is coming, which would decrease, kind of quench this pulsar wind. So one way it could increase because of the accreted matter, outflow of accreted matter, but accreted matter is very small. Accretion rate is very low, what I mentioned already. And then another way is this pulsar wind could hit the accretion flow, and that could create some gamma rays in the accreting phase. But problem is, if that happens, then we could not explain the X-ray pulsation because accretion would be stopped well outside the light cylinder, outside the magnetosphere. So we cannot explain the X-ray pulsation, the low inner edge radius of the accretion disk, and the 32% increase in the spin down rate. So these things cannot be explained. So these are the problems.
Can I ask you?
Yes.
If I remember correctly, you said that Lomax binary phase and the radio pulses, their magnetic configurations are different. Otherwise, you will not see a collimated thing and the accretion. Then why do you expect what is the magnetic field, the similar amount of magnetic field which has been observed in radio phase is the same as the X-ray?
That's right. So the thing is that what you have said and what earlier I said, that is generally believed. What happens is how the pulsar wind comes out. These are highly charged particles coming out of the neutron star surface because there is a huge voltage is created, and that can act against the gravity of the neutron star, which can pull the particles out. That's how the pulsar wind is created. Now, if accreted material, which is a plasma, that goes into that region is shorted, like our electric circuit is shorted. So that voltage is gone. So we do not expect the this pulsar wind in the accretion phase. But which I have not mentioned, and this is not, I have not mentioned so far because that is not studied, explored so much so far. The thing is that some people have studied that if the accretion rate is low, as for this particular source, as I mentioned, accretion rate is low, then the accreted matter can come, fall onto the neutron star, but the portion from which the pulsar wind is coming out, that portion, to that portion this matter is not going. So that portion is not sorted. So in such case, when the accretion rate is low, both the accretion and the pulsar wind can simultaneously exist. And we are considering that particular thing here. And I will mention a little more, I'll show a cartoon later. But that is the case here. So here is the here are the summary of some main problems. Why 5 to 10 times increase of the gamma ray luminosity in the accreting phase? Why 32% increase in the spin down rate in the LMXB, that is accretion state? What explains the X-ray pulsation and low inner edge radius of the accretion disk in the high mode? And if the inferred neutron star magnetic field is relatively high? And why are there two distinct and stable X-ray modes in the LMXB state? Now we'll see, if we start with the basic principle of angular momentum conservation or torque budget equation, these problems can be self-consistently and mutually solve each other. Now I'll describe our formalism. Here is the torque budget equation for the radio phase, RMSP phase, when there is no accretion. So this is nu dot, rate of change of angular momentum, which is proportional to the torque. And this part is because of the pulsar wind. This part is because of the gravitational wave. GW is gravitational wave, PW is pulsar wave. This is the total which we have measured. In the LMXB state, these two components may be there, plus there should be another component which is due to accretion. So these are all the components. So we have just formally written all the components. Some of these components could be zero, but we have formally first written them. And these are the measured values. And now, note that we do not a priori assume the non-zero values of this gravitational wave component, which means the gravitational components can be zero. We are not a priori assuming them to be non-zero. We have just put these terms in the equation.
So the electromagnetic component is in the pulsar wind, or that's, I mean, the nu dot due to the.
So pulsar wind contains the electromagnetic component. So you see that if it is only magnetic dipolar equation, it would be proportional to nu q. But if you consider also the pulsar wind in it, this instead of nu cube, it will be nu to the power n when n is slightly less than 3. Okay. So rather, first we will try to see in a direct way if at least one of these components, gravitational wave component, either in radio phase or in accreting phase, could be non-zero. And if yes, then in what condition? That is our aim. Our aim is to find out whether this source can emit gravitational waves, and if that explains the major observational aspects. So to do that, we a priori consider them to be zero. This could be zero, but then we'll see that the zero does not work. That is the way we will show that there must be some must have some non-zero values. So to do the simple calculation, because the accretion rate is small, this cannot, the accretion rate, accreted matter cannot contribute more than 5% to this. So for simple calculation, we put this to be zero, but later we will consider it accurately. And then these are the first two equations I have already shown, torque budget equation. Then I consider the energy equation. So in RMSP phase and in LMXB phase, this is SD is the spin down, and from the spin down which powers the pulsar wind and magnetic dipolar radiation, this is the L, that is luminosity or power. This can be written in two ways. This is the theoretical formula which connects it to nu dot, and here I consider that this powers the gamma rays. So this is the observed gamma ray luminosity or power in RMSP, and this is LMXB phase, and eta denotes the gamma ray emission efficiency, which means the entire thing will not become gamma ray. Some part will not be emitted in electromagnetic radiation, some part will go into X-ray, some part will go into radio. Mostly it goes to gamma rays, of course, that's our experience, but it will be less than 1. So this is the gamma ray emission efficiency. We take a ratio of these two equations, we get this. So we have three equations, these two and the bottom one, which I write here. And I put it in black because for the time being, I am ignoring it, it's small. Now these are the three equations, and this you see that if we ignore these gravitational wave components, because a priori we consider them to be zero first, then this is what we measure, because these two terms we have measured. If we ignore this, these are the two terms we have measured, and this is 32% increase, so 1.32 this ratio. On the other hand, this also we have measured, which have come to be 5 to 10, which implies that the gamma ray efficiency in the LMXB state is about 4 to 8 times higher than the gamma ray efficiency in the radio state, which we cannot explain. If we want to explain it, we have to consider possibly that the pulsar wind is hitting the accretion flow, stopping the accretion there, and from there more gamma rays is coming in LMXB accreting phase. But if we consider that, that will not explain many things. For example, spin down, the increase of the spin down, and X-ray pulsation, and X-ray inner disk radius very low, and so on. So this ratio can be at most 1 or maybe less than this. That's what we expect. But if we do not consider any non-zero value of this, we get this is to be between 4 and 8. So that is the indication that at least one of them should be non-zero. And I will consider it a little more formally now. So what I do is these three equations I have, the two torque budget equations and one energy equation. I combine three of them, doing a little algebra, and I get this equation. And this equation, this is color coded. You can easily see this is the equation of straight line, y equal to mx plus c. This is color coded, so you can easily see. This is y equal to mx plus c. And I plot y versus x, that is this versus this. And I take two values of this ratio here, which is 5 and 10, which we observe. And at the beginning, I consider in the LMXB state there is no gravitational wave radiation, so it is 0. If we do this, we find a straight line, and this is the straight line. And if we consider that this LMXB accreting phase gravitational wave emission is not 0 but equal to this value, then if we solve this equation, we get this dashed line. Okay, and that is considering this gamma ray ratio is 5. Gamma ray ratio is 5. And if we consider this gamma ray ratio 10, which is also observed, then we get this blue counterpart of this red thing. Now you see that this is this gravitational wave component versus this gamma ray efficiency ratio in the accreting phase to radio phase. And I said that this ratio should not be more than 1, maybe somewhat less than 1. That is, this green portion is allowed. But if you consider the green portion, you see that the nu dot due to gravitational wave, that is the spin down rate due to gravitational wave in the radio phase, must be non-zero. Must be non-zero. This is of course negative. Negative must be non-zero. Magnitude is non-zero. Okay. So this shows that there must be some gravitational wave emission in the this radio phase. And if there is some emission in the radio phase, that actually should not vanish in the accreting phase. So accreting phase, it should also be there. So before going into more detailed calculations, I consider a very specific example to estimate the mass quadrupole moment of the neutron star and the magnetic dipole moment. So I am not going to describe it in details, but I consider very reasonable values. Some of these are observed and some of these are some known values or expected values, just to see for one case what kind of magnetic dipole moment and the mass quadrupole moment of the neutron star and other parameters like R in, disk energy radius, and other things we get. So for putting some specific values, we get some of these values of mass quadrupole moment of the neutron star, which is about 10 to the power 36 in CGS, gram centimeter square, and ellipticity, which you remember that the mismatch in the neutron star radius in the direction perpendicular to the spin direction, and this fractional mismatch is only 10 to the power minus 9. We have considered some specific expected values such as moment of inertia of a neutron star, which is should be of this order that we know. So these are the parameters we have got, and along with this we have got some other parameters. Using this, we will now examine our particular formalism and how it can explain the complex observational features of this particular source. So implications of our formalism. So remember, this slide I am showing second time. So it summarizes the main problems. One problem was about the increase in gamma ray luminosity. Another problem was about increase of the spin down rate. Another was why two distinct and stable X-ray modes are there in the LMXB state, and only in the high mode we see X-ray pulsation, but not in low mode. And the disk energy radius measured from the independent X-ray spectrum analysis was low, and so on. We see, as I mentioned, that if we start with the basic principle of angular momentum conservation, this problem can be self-consistently and mutually solve each other, and that's what we will show now. Let's consider this X-ray two modes. So for the specific example, very reasonable one, we found that the Rm or Rin is about 25 kilometers, and RCO 24.6 kilometers, and RCO is about 25.4 kilometers. Therefore, this Rin or Rm is less than RCO in the high mode. We are considering high mode here, and therefore we expect X-ray pulsation, and that's what we observe here. Moreover, you see that completely independent X-ray spectral analysis, we find that Rin value to be this or this, and this matches with our value. Rm is basically same as Rin. So we find this very similar value. And therefore we can explain this high mode when Rin, that this energy radius is less than RCO, that this goes inside RCO, the co-rotation radius, and when we expect pulsation. So this can be explained, and note that we get these above two crucial consistencies, one about pulsation, another with the X-ray spectral analysis results. So our very simple calculation is consistent with two major independent observations, although in our formalism we do not consider accretion at all. Remember that we argued that it is 5% only. We have ignored that. We have considered other things. Still, we are getting the very consistent result, even without considering accretion. And then the low mode. Now we consider low mode. And for low mode, we expect that Rin or Rm should be outside or more than RCO. That's why we do not see any X-ray pulsation in the low mode. And that's what we get from our specific example. We get the Rin or Rm is 28.7 kilometer and RCO is only 25.4 kilometer. So Rm is more than RCO, and therefore in the low mode we do not see any X-ray pulsation. So we find that the two distinct and stable X-ray modes, that is also another big question. Why there are two distinct and stable X-ray modes like this, black and blue, for this particular source? The distinct and stable X-ray modes in the LMXB state are due to two regimes of the source, accretion and propeller. Propeller means when accretion does not happen, when Rm is or Rin is greater than RCO. So now we go for this gamma ray thing, and there it will answer your question. It shows via a cartoon This cartoon is not by us, but another group which did this simulation, and from this paper. See, how do we explain the increase in gamma ray in the accretion phase? What happens in the accretion phase? Accretion disk goes inside the light cylinder and it goes up to Rn, which is the disk NRH. All the magnetic field lines which were crossing in the, or at least most of them which were crossing the accretion disk would open up because the material there are moving. It takes the magnetic field with it because magnetic field is frozen in the plasma, that is accretion disk, and ultimately they break and they open. So they are opening up, and that opening up increases the number of magnetic field lines by a ratio which is typically RLC by Rm whole square, because whole square gives the area. So this much magnetic field lines are increasing, and that increases the pulsar width. And that is why we see a 5 to 10 times increase in the luminosity in the elementary state in gamma rays, which comes from pulsar width. So that is the explanation. So here you can see that this is not very well explored actually. I am telling again that part of the accreted matter is falling onto the neutron star, but this part is not sorted. The plasma is not going here. That's why the pulsar wind is still active. But this is not so far considered very widely. So here I show this by this diagram, the self-consistency of our formalism. The general Todd budget equation, we start with these two general Todd budget equations, which we do not question because it's the conservation of angular momentum. Plus, we consider something which could be questioned, that 5-10 times increase in the gamma ray luminosity in the elementary state is primarily due to the increase of the spin down power. Spin down power increases because the magnetic fields are opening up in the accreting phase. If we assume these two, we get a pulsar ellipticity because we find that these gravitational waves are emitted in the radio phase also, which means pulsar is slightly deformed. And if we consider the pulsar ellipticity, that gives us a low pulsar magnetic field, and hence that implies the accretion regime in the high mode and propeller regime in the low mode. That is the two regimes, two high modes and X-ray and low modes in the X-ray observation can be explained. And that in turn explains the same thing that is written here. That is because the accretion disk goes in the high mode very close to the neutron star, that opens up the field lines, and therefore that increases the spin down power and hence the gamma ray luminosity. So this chart gives the self consistency. It comes from here, starts from here, and this same thing can be explained here. And then the final thing, constant on the Mach quadruple moments. So now that we have set up our formalism, we think we have understood how the source is working, etc. What we have done, we have considered many initial parameter values and tried to constrain these values. So basically almost 2 billion combinations of input parameter values I considered, almost 2 billions. And I tried to find out what are the ranges of those parameter values which can reproduce the observed results. That's how I constrain the parameter values, various parameter values. Of course, I put 4 conditions. The 2 conditions I have already explained. That is that in the high mode, the disk inner radius is less than RCO, co-rotation radius. In the low mode, it is greater than co-rotation radius. And this opening up of the magnetic field lines can increase the spin down power by this RLC by RCO whole square, which I showed, which should be greater than the observed ratio of the gamma ray luminosity and in the elementary phase, accreting phase, and the gamma ray luminosity in the radio phase. So these conditions, these 2 conditions we observe. There is another condition which comes from the optical observation of the irradiation of the companion star, which I am not explaining. And then there is the theoretically estimated possible range of the moment of inertia of a neutron star, which I take this range from another paper. my old paper, that is it's a theoretical estimation. So with these four conditions, I can constrain all these parameters. I took almost 2 billion combinations, and you see that when I put this condition, that is gravitational wave spin down rate due to gravitational wave in accreting phase is equal to the spin down rate due to gravitational wave in the radio phase. I put this condition, then I get this. I also got the accepted ranges of other parameters as well, but these are some of the main parameters. The magnetic moment of the neutron star, the magnetic field of the neutron star, the surface magnetic field, the mass quadrupole moment of the neutron star, and the ellipticity of the neutron star. You see the ellipticity, the magnetic mass quadrupole moment comes out to be of the order of 10 to the power 36 gram per centimeter square. We found it earlier also, but we got a specific value. Now we got a range, and for this particular source, and ellipticity is in this range, but it is in the same order, 10 to the power minus 9, which means that if the neutron star radius is about 10 kilometer, the excess radius is of the order of 10 micrometer, because 10 micrometer divided by 10 kilometer is 10 to the power minus 9. Okay. Now this is due to this condition. I relax this condition. Sometimes people say, well, when the matter falls onto the neutron star in the accreting phase, low mass extra-binary phase, it increases the ellipticity. And therefore, I consider this condition that in the accreting phase, nu dot could be either greater. It is the magnitude I am considering, just the magnitude. It's greater or equal to the spin down rate in the radio phase. If I consider this, this is the ratio of mass quadrupole moment I have got. The order is same, but this is the range I have got. And then I lift all mutual conditions. I do not consider any mutual condition. The nu dot GW in accreting phase and nu dot GW gravitational wave in the radio phase can be anything. They are mutually unconstrained, mutually free of each other's effect. Then I get, these are the ranges. That is, in the radio phase, this is the range of the order of 1. In the accreting phase also, it is of the order of 1, but a slightly larger range in the accreting phase. The important thing to notice here is this. This is the lower value. The higher value is not that important. Lower value is non-zero. That is the important thing. If it were 0, it would be consistent with no gravitational wave emission. However, it is not 0. In both cases, when they are mutually independent of each other, then also we get the non-zero lower value for each case, in each state, which means in each state, the neutron star has some non-zero ellipticity, which means it must emit some gravitational waves in both states, and that is the important result. That is why people are interested in this result. And now this is the last slide. So here I come to the fun page, the amazing fact. So the excess radius, you see, that is only 10 micrometers, which is same as the size of a bacterium. So you see that the extent of the neutron star is about 20 kilometers, and in one direction radius is only slightly more, about 10 micrometer more. And the fun thing is that we are talking about measuring the size of a bacterium from a distance of about 4,500 light years. And let me tell you, this is far, far more difficult than measuring the size of a dust on Pluto from here. So that's the end. And here I stop. Thank you.
Questions? Everything was crystal clear.
Oh, I think there are
So
questions.
Moitra has a question.
Yes, so